the title of the talk was already mentioned by Sergey. So this is this talk contains results of several authors. So the first part, in the first part, I will present some published work with Vladimir Miller a few years ago, and then some consequent work which is currently submitted, and it is joint work with Syed Mahmoud Manigani and Horsha Kusal-Yogi. Probably I didn't pronounce it correctly, but hopefully I was not too far. And the second part is on infinite matrices, and it's and it's also part of the paper which is in preparation for submission, also with Vladimir Miller. Okay, so if something will be, this is perhaps too close. If you have problem with some to see something, please let me know so that I can correct it. Okay, so let's continue. So first, perhaps some minor introduction on max algebra. So it is also known, so the larger field, it is also known as tropical algebra. So max algebra is an algebraic system which is very useful for describing certain conventionally nonlinear problems in a quite linear fashion. So these problems appear in several areas. Some of them are machine scheduling, discrete event dynamic systems, combinatorial optimization, mathematical physics, information technology, DNA analysis, graph theory, and others. So today I will present results in max times algebra, but there are other well-known, I think also for most of you, I would say, or all of you, algebraically isomorphic versions, so as max plus algebra, min plus algebra, and generally all of these isometric algebraically looking semi-fields are known as tropical algebra. So whatever you prove algebraically in any of these fields hold also in the other fields, and the translation in the other language is usually quite straightforward, although sometimes it can be a little bit how to say, sometimes it needs to take time to translate some results into other, but it can be done usually quite straightforwardly. So as I said, I will usually use the term max algebra for max times algebra. So this is a semi-field. It's a semi-field which is defined by a set of non-negative numbers and two operations. So for the product, we take the usual product with non-negative numbers, and for the max summation, we take just the maximum of two non-negative numbers. So and now what we do is that we use usual linear algebra ideas, just replacing usual plus with this max, with this plus, so the maximum, and the usual product stays the same in this setting. So by this notion that A is more or less to zero, we will denote entry-wise non-negative matrices. Similarly, denoted like this, X denoted like this, so means that we take non-negative vectors, so entry-wise non-negative vectors of dimension n. We will use, sometimes we will use a little bit different notions for the entries of the matrix like this, dependent of what we need them for, or so that the layout of the is more clear, perhaps. Okay. So with some additional notations, we use, if we have two non-negative matrices, n by n, let's say, the maximum of this, the max sum is just defined entry-wise as the maximum of the entries, and the max product is defined like in linear algebra, just by replacing the usual linear algebra or the standard operations with this max algebra operation. So the plus is replaced by the maximum, and the product stays the same. So this is how we define the product of two matrices, compatible matrices we can take here for our uses, and by n matrices, both of them. So again, the multiplication. So again, this is the same notation that is usually used for the Kronecker product of matrices, but we don't mean here the Kronecker product. This is just the usual notation in tropical mathematics, quite usual notation for a max product. So we use this notation here. So this is not a Kronecker product, right? And similarly, we use here this notation for the product of a matrix with a vector. So again, they need to be compatible. Again, replacing the plus with maximum, and the product stays the same. So we use this notation for the max powers. A to the power 2 in max algebra is this, and similarly, more general powers. Usual associative distributive laws hold in this semi-algebra. So algebraically looking, this is a semi-algebra. So, or also if square matrices, let's say, form semi-algebra here. So the point is that inside max algebra we don't have the natural minus, but we can extend this semifield to several larger semifields where you could add some other at minus, so some subtropical algebra or other versions of these generalizations, but we will not use this here. Okay, so the spectrum in max algebra, we will denote it like this. So we mean here geometric spectrum. This is called the geometric spectrum in max algebra is noted like this, and this is the set of max eigenvalues. So these are non-negative values, such that there exists non-negative vector, which is non-trivial, such that A times X is lambda X. As usual, just replacing the usual, the product here is our max product. So in max algebra, the role of the spectral radius is taken by the maximum cycle geometric mean. So we denote it like this. It's not a very nice notation, but okay, I will still use it here. So the spectral radius in max algebra. So what does mean maximum cycle geometric mean? It means exactly as the word means. So we take here, see, we take the cycles, we take A1 to E1 to E2, and then sorry, at the moment I forgot the letter. I, right? I1.
I, yes.
Thanks, Harry. I1, I2, I2, I3, and so on. And then we have a cycle. We come back to the I1. So IK, I1. And then we take, so these we multiply here k numbers, and then we take the cut root, and then we take the maximum of all of this, and this is known as the maximum cycle geometric mean. In the definition, we can also say that we can take mutually distinct indices here, and this can be proven that this is the same. Okay, so the Mach's version of Perron-Frobenius theorem states that this maximum cycle geometric mean is the largest geometric eigenvalue in max algebra. So, and if A is irreducible, then this is the only eigenvalue, and every corresponding max eigenvector is strictly positive. We can also speak about the basis in max algebra of the corresponding eigencone, but I won't speak about this here at the moment. It is also known that the max algebra version of the Gelfand formula holds. So this is a short name. Some other names could be included here, but so short version of the Gelfand formula. So that this is that maximum cyclic geometric mean is the limit of these notions here. So the norm of the kth power and then taking the kth root. And since all vector norms in real or complex matrices are equivalent, we can take any vector norm here, right? But we will usually take here the entry-wise maximum, which in general we would take the maximum of the absolute values of the entries, which is a vector norm, but for non-negative matrices, this is just the maximum of the entries, right, of the matrix, and this is we use here this vector norm here. Okay, so now let's talk about the description of the max spectrum via local spectral radii. So, okay, we will use this notation. So as I mentioned, I will use this notation for the norm, just the maximum of the values of the matrix, and similarly for the vectors, right? Good. And then this is just the local spectral radius in max algebra at x at a vector and a non-negative vector x. This is just a version of local spectral radius, a standard local spectral radius from classical linear algebra. So in classical linear algebra, you take here arbitrary, so usual powers and usual product, but now here we take max operations. So we take here the upper limit of these values. And it is well known that, or perhaps it's not so well known. So perhaps it's not that well known. So it was proved in our, perhaps this is not so well known, that it was proved in our joint paper with Vladimir Miller. He was the main contributor of this, and some also many other things that I would speak in this talk related in our joint paper, that the limit here is that the limit here exists for any x non-negative, and of course also for x is 0. And for any x that is non-zero, the following holds. So this that the local radius at x is the maximum of local radii corresponding to the standard vectors, right? So I hope that it's clear what standard vectors mean. So EI means that we take 1 at the ith entry and zeros elsewhere, right? The classical standard vectors. So just 1 at the ith entry and zeros elsewhere. And the local radii of x, when x is non-zero, is just the maximum of the local radii of the standard vectors for those entries of x that are non-zero, right? Okay, so if we look at this definition, you take here the RIGA means that you take here the standard vector. So this means in the matrix AK, the ijth entry means the maximum weight of the maximum weight of length k from the node I to j. And so if we take here the ej, then we take here the jth column of this matrix. So this translates to this, what is written down here, that this norm of this, what is included here, is just the maximum weight of length k of all of the entries that end in j, right? That end in j. So you look at all the paths, and you look at the ones of length k, and you look at those paths that end in the node j, and the maximum of these weights of these paths is exactly this entry here, this entry here, and then you take here the cut root and take the limit, and you get rej, right? Okay, so I think in '94, or at least the paper I think was published then, Gunawardena studied the cycle time of vectors of max plus linear maps. So in max algebra, this is this vector. So it is this vector with the entries, the jth entries, is just the limit of a to the power k times j times the vector y, then taking the jth entry of this and taking the cut root, where y is any vector in the interior of the positive cone, right? The standard positive cone. And it is known that this limit is independent of the point of the choice of j. So we can take, let's say, the vector of only one, so 1, 1, 1, 1 in any entry. And it is not hard to check that our, what we were speaking before, Raja is just the jth coordinate of this, of the cycle time vector of the transpose matrix, right? And this can be seen here. So by definition, so since we take here the maximum in the cut column, this can be this is just this max multiplication with the vectors of with the vector 1, right? With the vector of all ones, then you can take the transpose at the transpose, and so this we get it reverses. And now if you look at the definition, this is the definition of Rej. We use this, and then we clearly see that this is exactly what we stated above. So perhaps I'll wait a bit if somebody is thinking about this. Okay, perhaps we continue. And so the theorem of Gunawardena is then, so at the time when we published this paper in 2015 or a bit earlier, I was not really aware of this, that this, what was proven here was already known by, even though I suspected that it was somewhere known in tropical mathematics, but I could not point out the result to anyone. So, and the proofs that we used in 2015 were much more linear algebraic as here, and the result means that why are these Rej important to us? Because these are exactly the geometric eigenvalues, right? So the max spectrum are exactly those lambda that are equal to Rij for some j. So all Regen or Ej are exactly geometric eigenvalues. So you can take any here, but of course for different for different IEJ, you can get the same value. So in general, you have less eigenvalues than n. But okay, you could count somehow multiplicity here also in some sense. I don't know if this is sensible, but perhaps it is, that you count how many times lambda is obtained by some standard vector like this. So you could define this as multiplicity in this way. Okay, good. So the following lemma, which could also be translated back to Ljubljana probably, although this was a very nice direct linear algebra proof by Vladimir, who obtained this with a very nice proof that that Rej is exactly so. If you read this, it's a bit complicated, but I'll try to explain here with a picture. So Rej is the maximum of the following lambda that satisfy the following property. So what does this property say? Okay, so I didn't speak about this before, but I was using the terminology here of graphs. So given a non-negative matrix, we can define here an associated graph, so that 1, 2 to n are the nodes of the graph. And so this is a weighted graph, a directed weighted graph, or a D graph. And we say that there is an edge from I to j if and only if Aij is strictly positive. And so using this, what is written here can be drawn like this. So you look at the cycles. You look at the cycles, and you look at those cycles where lambda is attained as a cycle geometric mean. This is what this means. You look at those cycles that lambda is the same as the cycle geometric mean of such a cycle, and then you look at those cycles that have access like this to j, right? And what this lemma says is that Rej is the maximum of those cycle geometric means that have access like this to the node j. So this is what this lemma says, and these are exactly the eigenvalues, the geometric eigenvalues of max algebra. I didn't speak here about algebraic eigenvalues in max algebra, which are the tropical roots of the associated characteristic polynomial. But it is known, for example, that all geometric eigenvalues are also algebraic eigenvalues, but not vice versa. You can have algebraic eigenvalues which are not geometric. But we speak here about geometric eigenvalues. So, okay, this is what I somehow translated, that that these eigenvalues are exactly the maximum cycle geometric means of those cycles that are such that the node j is accessible from these cycles. And then because these cycles give us eigenvalues, right? This is sometimes called, these cycles are called lambda critical cycles, because or also they could be the spectral cycles, because they give us the eigenvalue. Okay, so now let's shift a little bit to the classical setting. So now we look at the classical linear algebra setting. I was kind of raised in linear algebra, so this is the setting that I feel more comfortable in even now. So, but let's look at some analogs. So, let's have a complex n by n matrix, the standard complex matrix, and a complex vector. Then the usual local spectral radius is defined like this. I don't know if here the limit exists. I don't think so, but I'm not so sure. So, and I would be very interested in the exact characterization of when exactly for which matrices this limit exists. This is at the moment not clear to me, but this would be quite useful also for me. So if anybody knows, I'll be thankful for some reference. So we take here usual powers, usual products. So, and sigma A is just the set of usual eigenvalues, so the standard spectrum of a matrix. So with similar proofs, as I didn't speak here about the proofs, but with similar proofs as we used in this paper in linear algebra and applications, this was published, we can have the following related result, which is probably also known somewhere, but in Perron-Frobenius theory, but I don't have the exact reference when was this firstly proved. This is why I put here 3 dots. If again somebody knows where exactly I can put this, I would be also grateful for this. But okay, it was also proved in this paper in 2015. If you have a complex matrix, then the absolute value of all the standard classical eigenvalues are just exactly the all t that are the local radii for some x. Okay, that are the local radii for some classical local radii for some vector x. And now we can speak about distinguished spectrum, which Sergey knows quite a lot because he did a lot of also research on this. So the distinguished part of the spectrum are those classical eigenvalues, non-negative eigenvalues, that correspond to non-negative eigenvectors. And for example, this it is sometimes very useful to get non-negative vectors. This, in more generality, this would be called Krein-Rootman theory, because, for example, it's useful in economics and elsewhere. So people are often very interested about those eigenvectors or eigenvalues that correspond to non-negative eigenvectors. For example, if we take a non-negative matrix, then the spectral radius, the classical spectral radius, the largest eigenvalue, is such an eigenvalue. So this distinguished part of the spectrum is always non-empty. Okay, so what is known is that if we and what was proved in our paper in 2015 with Vladimir Miller, it was proved that the distinguished part of the spectrum are exactly those lambda that are obtained by the as a local radii corresponding to standard eigenvectors. So again, I wrote here 3 dots because probably this was known before, but I don't know the reference. So if anybody knows it, I would be grateful. But it was also proved in our paper with similar methods as the previous proof in max algebra, and I would be grateful for some reference if somebody knows it, because I would guess that this is standard, but I don't know. Okay. So now let's speak about connect. So see, we have here quite a nice analog, and let's speak about some analogs, some connections, some asymptotic formulas between the max spectrum and the distinguished part of the spectrum. And this part will be from our joint work with Mahmoud Manegani and Horshakus Yogi. So let A be a non-negative matrix, and let rho of A denote the usual spectral radius of A. So this is just the maximum of the absolute values of classical eigenvalues. And so the well-known Gelfand formula states this. And it was also, it was proved, the following important formula was proved by Elsner and his co-authors. that the largest max eigenvalue is less or equal to the largest, the absolute value of the spectral radius, and this is less or equal to n times the largest max eigenvalue. So, and this can be used, this formula 1 can be used to get some nice asymptotic formula between these largest eigenvalues in the max algebra setting and in the classical setting. So it is known that for non-negative matrix, this is always an eigenvalue, right? Good. So let's speak about now the simple powers, right? The Hadamard Schur powers. So we take the students' version of the power, right? The one that students like because it's easy, and I also like it because it's easy and it's useful. So, and it's also quite useful in many applications. So it's not artificial. We take the anti-wise power here, which is known as Hadamard or Schur power. T can be here strictly positive, but usually we will use T larger or equal to 1. But so let's take the Schur power here, and it can clearly from the definitions this fact follows for the largest eigenvalue. And by using this inequality, if you take here the Schur powers here and using this, you can quickly get this equality, which I don't know who's, I'm not exactly sure at the moment, was it proved by Friedland perhaps for the first time, or perhaps by Schneider 15 years earlier. I'm not really sure at the moment. I didn't go to check again all the references, but perhaps it was also already known by Hans Schneider in 71. I'm not sure at the moment, but for sure I think it was proved by Friedland in 86. Okay. So I mentioned before a bit algebraic eigenvalues. So I was not correct when I said that I won't speak to it at all about algebraic eigenvalues. I will mention some of them, but I won't speak about the exact definitions here. So the algebraic eigenvalues of A are the tropical roots of its max algebraic characteristic polynomial. So you can define characteristic polynomial in a similar way as in classical algebra, just that you use, instead of the determinant, you use the max version of the permanent, and then the algebraic eigenvalues are those values at which this polynomial is non-differentiable. So it turns out there are exactly n algebraic eigenvalues counting suitable multiplicities, and it is known that all geometric max eigenvalues are also algebraic eigenvalues, but not vice versa. And this result was proved by Akian, Gobert, and Bapat, but I think in a max plus setting. But I never quite could relate to this result before I translated it to max times, and then it was for me quite easy to state it, so quite easy to read it, let's say. Before in max plus, it's hard for me to read it, even though you can read it, but I couldn't really relate to it. And it says the following: this is the description of algebraic eigenvalues in max algebra if we by the classical eigenvalues of a suitable matrix. So we take here the non-negative matrix, okay, and then take the Schur power for T, okay, for T positive, take the Schur power, AT, and these algebraic eigenvalues in max algebra are obtained exactly like this. So these are the limit as T goes to infinity. So we parameterize metric in such a way with a new parameter T, and then we take the classical eigenvalues of this matrix, and they take the third root and also absolute value, and then they take the limit. And it turns out that these are exactly algebraic eigenvalues. And then I started to wonder, does can do. So we know that, okay, we can, on the right side, we have distinguished eigenvalues also, and here we have geometric eigenvalues. So do these correspond? And yes, the answer is yes. The answer is yes. And the similar results holds also for singular eigenvalues. On the right side, you take singular values, classical. On the left side, you take the max version of this, of singular values, and similar correspondence hold here. And then I was thinking about correspondence with distinguished eigenvalues and geometric eigenvalues in max algebra, and it turns out that exactly they follow this kind of formula. Let's talk about this. So okay, first let's the following lemma is quite direct and easy to prove. Just an exercise for all of you. So you can take the out of the norm here because you just take the maximum, and also this holds directly for definition because you have maximum. You can take the powers outside the sure powers, and then consequently also this holds. Okay, and the following theorem, which is currently not yet published, it is in submission, is so this is one of the papers. This is one of the results from the paper. That we have this, that the geometric eigenvalues in max algebra are exactly obtained in this way. In this way by the distinguished eigenvalues, of the sure powers of eta. So it's not surprising that the results on these eigenvalues are so similar if you look at them, like Sergey with his co-authors, for example, Hans Schneider and Professor Katz, proved several results that show that there are a lot of similarities between these eigenvalues, and it's not surprising because you can probably use this formula and translate one theorem to the other theorem directly. Often, I would say, probably. So I think this is quite a useful tool for translating results from one setting to the other. And so, and the proof is also not difficult. Just the question one should think about this: should this hold? And then just to verify it, the proof is quite direct. So it's like this. Then you can quite not too hard. It's not too hard to check that this holds, and then by the previous lemma that we discussed before, you can do this, and then take the t out, and then just take the fifth root. Then just take the fifth root and taking t to sorry, not the fifth root, the mth root. The mth root, which is for the powers of matrices. Taking the mth root, then we get this. And now taking the fifth root and third to infinity gets this result. And if you go slowly, what we exactly prove, we could perhaps do it more nicely. We could first state the following proposition, that quickly we can verify this from the definition. This was what was done upstairs, and also that this version for any max geometric eigenvalues and distinguished eigenvalues hold, and then using this, that you take it for then plug in here. The proof was that what we did upstairs was that we plugged in here AT, and then use this on the left, on the right, and taking to infinity and get the result. So the following inequality is also known. These are classical products. This was from a joint paper with Roman, my PhD supervisor, my former PhD supervisor. I'm a bit bold for being a PhD student, so And so and also and so similarly one can show this inequality. So for the max eigenvalues we have equality here, and for distinguished eigenvalues, classical distinguished eigenvalues, we have inequality here. And then we can prove some additional results, some additional asymptotic results by using this. You can prove here that also in the limit upstairs here in this limit, sorry for jumping, you can take here the infimum, also this sequence here, also this, not the sequence, but this is decreasing in t, and that if you take here also, if you put in 1 divided by n, so the dimension of a matrix, then this is also the supremum. So this can be proved quite directly, and then we can prove some related asymptotic formulas between in a similar way by using similar tools. So for example, you can plug here also max powers. You can also plug here max powers and cut through it and take in the limit, and you again get max eigenvalues. And here is also the infimum, but here it's not probably it's not decreasing. I didn't go through all the checking, but I would suspect that not. And then this again, if you take divide 1, and this you get here the supremum. So from here you can talk about, you can use then here for about some lower and upper semi-continuity, then about the continuity of this. You can use it. These formulas can be used also for this kind of stuff. The following formula in the other way, right? What if you go from the other way, from max eigenvalues to the classical ones? This was known about the largest eigenvalues that this formula holds was proved by Papat. So this formula said that you can, in the Gelfand formula, you can take also, instead of the norm, you can take here the maximal geometric mean, so the largest max eigenvalue, right? And it is known that this is not in general increasing in K. And then, so again, this follows from the previous inequalities that I was talking about, and you can also think about it. Also, this holds. You can here you get the supremum. K, AK are here the classical powers, right? You take the something in max algebra, and this is classical. This is classical, but then you take the maximum eigenvalue of the classical power, and then you also have here suprema and infima like this, and then you can and then we have also this result. I was trying to prove a stronger version of this result, but I'm not sure if we can. So if anybody can improve it, I would be grateful. All I could prove was this. So this is in our joint work with my co-authors here. So okay, we have in general, I think we have only inequality here. I would suspect that we don't have equality. If somebody can prove that there is equality here, I would be grateful, but I'm not sure if it holds. And then the result is like this. So this is not an asymptotic formula as well I was like it, but this is all we could prove, is that for each I and each M, there exists such J and such an infinite sequence, so a subsequence of powers, right? A subsequence of powers, which is increasing, such that we have the limit here that the distinguished eigenvalue corresponding to EJ is the limit of over this subsequence over some AJ, right? So this follows from Sergei might guess it because it follows from his joint from his result with Hans Schneider and Professor Katz, and you can and then you can take also the infimum here. So if anybody can improve this, I would be grateful. Or perhaps it can be improved, but I'm not sure. I would like to have here a nicer formula, but I can prove only a nicer formula under additional assumptions for for A, but for general A, I could prove, we could prove only this. I didn't know how to improve this. So under additional assumptions, let's say if the spectral classes are different, so if we have distinct eigenvalues, then we can have a better formula, but in general, I don't know how to prove this more better. Okay, it seems that I'm a bit out of time, so we can have, so this would be perhaps another talk again. We have some additional result for infinite matrices. We can have some nice, let's say, additional result to generalize some of this setting to infinite bounded matrices. The ideas are here that you take, again, entry-wise non-negative infinite matrix, so infinity and infinity, and then take the supremum norm here, and then look at the Banach space of bounded sequences, and look at the cone, which can look at it as a max cone of bounded non-negative sequences, and like this. And in this setting, then we can speak. We can have some results on the, let's say, distinguished approximate spectrum, not so much on the distinguished spectrum, but on the distinguished approximate spectrum. So perhaps let me just write it. Let me show this definition, what distinguished approximate spectrum means. Where do I have it? Sorry, I jumped it. So yeah, so approximate point spectrum is the set of those eigenvalues such that the infimum of this is 0. So this means that there exists a subsequence that in approximate eigenvalue are those S such that there exists a sequence of norm 1 vectors such that this difference, the limit of this kind of difference corresponding to those eigenvectors is 0. And we have additional results, let's say, of this, and something also on the eigenvalues. So this we call here point spectrum. But I won't go into more details, so let me stop here. So if somebody has some questions,
please. Okay, so does anyone have any questions then? You can unmute yourself and ask.